So what is constrained optimization? So I have some function of several variables, let's say a function of two variables, and I want to find where that function of two variables reaches its maximum value or its minimum value among all of the points in its domain, which also are constrained by some other equation, which also are part of a level set of a function of two variables. In other words, let's just look at a quick example that's going to take us into our preview activity for today. If in this preview activity, what we're doing is figuring out, it's one of these classic calculus optimization problems where we have a package that we want to send through the US mail, and the package has a square cross-section of side length x, and it has a width of length y. And so it's an x by x by y package that we want to be able to send. And the Postal Service has a restriction on what the largest possible parcel that you can send with a certain method. That restriction tells us something about the girth, and the girth is the sum of the sum of the perimeter of a cross section added to the height of the box. And so in the setup of this problem, what we end up saying here. And so the restriction says that girth, the sum of the perimeter of a cross section plus the length, has to be as large as possible, and the largest that this particular method of mail can do is 108 inches of total girth. Right? So what we're trying to do is find what is the largest parcel that we can send with this particular method. And largest here is going to be in the sense of volume. So we've constrained the length, width, and height of our parcel by saying that the girth has to be equal to 108 inches. And we want to know what is the largest volume of such a box that we can send through the mail. And so there are two functions at play here. One of them, in this case the volume, is called our objective function. That's the function that we're going to try to make as large or as small as possible. Right? It's the thing that we're optimizing is what we call our objective function. But then there's also another function, the function that computes the girth of our box, that gives us a constraint on the values of x and y. So we call that a constraint function because we want to find the largest value of the objective function among all points in the xy plane for which the value of our constraint function is being held constant to 108, for example. And so in a 2- and 3-dimensional picture, the constraint equation defines for me a level set, so a set of points in the xy plane. I'm going to move my head a little bit here so we can see everything that we're doing. The constraint defines for us a curve, in this case a straight line, in the xy plane. And it tells me that we're only going to look at those x and y values that lie along that line in the xy plane. So they all have to satisfy 4x plus y is equal to 108, right? So we only get to pick points along that line. And then from among those points, how do we find that point which has the highest value of my objective function? So it's a bit like looking at the 3-dimensional picture on the right and saying, how do I find where on my lines worth of points in the xy plane that we are reaching the top of that trace. So the trace of the graph of my objective function taken through the x and y values that are defined by my constraint. How do I find the top of that mountain? So just of that slice of the graph of f of x and y. So that's what we're doing when we're performing constraint optimization. So in this preview activity, we want to try to figure out how do we use both the objective function, the thing that we're trying to minimize or maximize, and also our constraint function, the thing that's defining for us what values of x and y we're able to choose from among. How do we use those two functions? Because each of those is going to be a function of x and y. They're both functions of two variables. How do we use those things to tell us where the top of the mountain or the bottom of the valley along that constraint equation is going to be? So what this problem does is it gives us a plot here which shows us some contours of the objective function. So the objective function, again, is the volume of the box, which is x times y. Here's some contours of it. So for example, this leftmost blue contour here is the set of all x's and y's that give us a box that has a volume of 1,000 cubic inches, right? And then here are all of the points x and y that have a volume of, give us a box with a volume of 5,000 cubic inches, and so on and so forth. Right? So those blue contours are contours of our objective function. Then this red straight line, that's our constraint. This is a set of all points x and y for which 4x plus y is equal to 108. Right? So these are all of the lengths and widths of our square cross-section box that give us a total girth of our box of 108 inches. So we only get to choose our x's and y's from among the points that are on the red line. And so your job is going to be to figure out, how do we find the top of the mountain? How do we find the largest possible value of the blue function from among the points that lie on this red line? So in addition to the pictures that are a part of this exercise out of the book, I also have a GeoGebra worksheet that's linked in your activity stream for today. So in the GeoGebra worksheet, we're seeing the contours, again, of our multivariable function. We're also seeing this straight line, that's our constraint. And then by dragging this plus around, you can choose different points that lie along that constraint. And it shows you the coordinates of the point. It shows you the value of the function, in other words, the volume of the box at that point. And it also sketches the gradient vector. At least it sketches the direction of the gradient vector of my objective function at the points in question. So by dragging this plus around, you can get a sense of how these things are all related to one another. So don't be shy to use this as a tool to help build your conceptual understanding as this activity goes along. And so the ultimate goal of this preview activity is going to be to figure out what relationship between the gradient vectors of our objective function and our constraint function is going to show us when we might be at the top of the hill or the bottom of the valley, the highest or the lowest point on the graph of my objective function from among those points which lie along my constraint. So to finish this activity, you'll just see if you can figure out the relationship that the gradient of our objective function ought to have with our constraint at the point that maximizes the value of the objective function f.
Greatest increase.
The direction of greatest increase. Since the gradient points in the direction of greatest increase of my function f, it's always pointing uphill on the graph. But I can't necessarily walk uphill or downhill. I have to walk along this black line, right? And so if I'm at a point where my gradient vector, my compass, is pointing me uphill, right? But I'm at this point, and I can only walk sort of upwards or downwards along this black line. What is the relationship between the gradient vector of f and the constraint line itself at that point? So you said that the contour and the constraint are parallel. What about the gradient of f and the constraint? What are they? What's that angle? So the gradient of f is perpendicular to my constraint at this point. And so what that tells me is that whether I walk to my left or to my right along the constraint, either of those directions is going to be a direction along which the directional derivative of f, my objective function, is equal to 0. Why? Because the directional derivative is the dot product of the gradient of f with the direction that we want to walk. And so if the direction that I want to walk, which is always along the contour here, right, along the constraint, if that direction is perpendicular to the gradient of f, that must mean that the directional derivative in that direction is 0. And so I've reached the top of the hill on the graph of f. If we drew the tangent line to the graph that goes in the direction, the only direction that I'm able to walk at that point along my constraint, that tangent line in 3 space would be horizontal. So the gradient needs to be perpendicular to the constraint because the constraint and the contours of f are tangent. And as you correctly point out in your write-up, that must mean that the gradients of f and g are also parallel at that point because each of the gradients of f and g are perpendicular to the contours of f and g. And so if the contours are tangent to one another, then that must mean that the gradients are parallel to one another at that point. So at our optimum point, the gradient of f and the gradient of g need to be simply scalar multiples of one another. So one of them is k times the other one. And that gives us an algebraic criterion that we can use to try and solve for those optimum points. So what I want to do to wrap up this preview activity is go a little bit further than the activity went and sort of talk through the algebra of what it might look like to find the coordinates of this optimum point. So my little GeoGebra tool here is telling me it looks like it's about 18, 36 is probably the top of this particular hill that we can get to on this constraint. So what would the algebra look like for us to actually have found that optimum point? So the authors of our text give us the traditional method for doing the algebra, which turns it into a three-variable system of equations problem. It's not the only way to do it, but it's sort of the most traditional way because you're solving for an x and a y, but you also have to solve for this unknown value k. That unknown value k is called the Lagrange multiplier. So that proportionality constant between the gradients of f and g at our optimum point is known as the Lagrange multiplier. And so we have to solve for that in addition to solving for x and y if we're using the traditional method. But then I have an alternative method that we'll also sort of look at afterwards. So traditional method. Solve the above for x, y, and k. If we're following the traditional method, we just have to set up this equation. The gradient of f is a k times the gradient of g. What it ends up giving us is two equations that bind x, y, and k together, which usually is not enough to completely determine the points x, the values of x, y, and k. And so the third equation that binds x, y, and k together is our constraint, right? Because x and y have a relationship to one another that's given by the constraint, which in this example is 4x plus y equals 108, right? So that ends up furnishing our third equation that binds x, y, and k together. And that should, with enough legwork, give you the ability to solve for x and y, which are ultimately what we're interested in. And the Lagrange multiplier itself, k, it has an arcane interpretation that I don't usually like to talk about in our calculus class. Usually, I just end up throwing that k away. It's there to help us find this optimum, but in and of itself, we don't necessarily care what value that k has. So, using the traditional method for finding this optimum ends up giving us this system of three equations. That when we set the gradient of f equal to k times the gradient of g, we get 2xy equals 4k, x squared is equal to k, and then the third equation is the constraint, 4x plus y is equal to 108. Solve those together, you end up getting x is 18, y is 36, and k, again, this sort of difficult to interpret parameter called the Lagrange multiplier has the value of 324. So let me offer an alternative to that traditional method. And I kind of like this alternative for a few reasons, one of which is that it bypasses the need for that proportionality constant k, so we don't have to introduce another variable into the process. Another method. So this other method relies on vector geometry a little bit more in a different way, right? One way of detecting when two vectors are parallel is to detect that one of them is a scalar multiple of the other. But there's another way to detect when two vectors are parallel using one of our vector products. So which of our vector products could specialize in telling us when two vectors are parallel? Perfect. So we can use the cross product of two vectors to detect when their vectors are parallel, right? So instead of introducing this constant of proportionality, this k that we're ultimately just going to kind of throw away anyway, we can use the cross product and test for where it is 0. Now, the wrinkle, of course, with that approach is that the cross product is something that we only know exists in 3 dimensions as the vector cross product and in 2 dimensions as the scalar cross product. So in this particular example, we're going to use the scalar cross product, which is really just the magnitude of the vector cross product if we think of the vectors as being in xy plane sitting inside of xyz space. But either way, if we just take the cross product of our 2 gradient vectors and then set that cross product equal to 0, then that, along with the constraint, will give us 2 equations in the 2 variables x and y that we can use to solve that. So for this, just compute the cross product of the gradients of f and g. So using the cross product can be a little bit quicker way to do it, potentially. Sometimes the algebra gets a little bit more challenging. It really does depend on the form of your objective function and the form of your constraint function. In this example, because the constraint ends up being just a linear function, 4x plus y, right? That makes it so that we can use the constraint equation to solve for one of the variables in terms of the other one, and then make a substitution into the equation that we get by setting the cross product equal to 0. And so, again, that gets us to the same solution that we had before, x equals 18, y equals 36. So at this point, 1836 really is the top of the hill along this constraint of the objective function. And this is a way to get there without having to introduce that auxiliary third variable, the Lagrange multiplier, that we end up not really being interested in the interpretation of anyway in the process.